So in our introduction to exponential functions, it says Mr. Raymond wrote the examples of a linear and an exponential function. So here they are. What do the equations have in common, and what do they have as a difference? So we're looking for commonalities and differences. Okay, so just look it over. Doesn't have to be for long. Just the obvious stuff. Let's see, what do they have in common? Let's see. Well, what is it composed of? What numbers or variables? Do you notice? Like the linear function, what does it have? And the exponential function, what does it have? Okay, it has an exponent. That would be a difference, but what do they have in common? Yes. Oh, okay, so it's a different function. Again, that's a difference. How about they're both functions, right? This is function notation, f of x and g of x. They're both functions. Anything else? Look at the numbers themselves. They both have 2 and x. There you go. There's some commonalities. They're both functions. Okay, so they follow the rule for functions, and they both have 2 and x. And for differences, we already talked about one has an exponent. That's a difference, and one doesn't. Anything else that's different? Oh, okay. One is a f of x, the other is g of x. So they're functions, but they're not the same function. So they're different types of functions. Write some of this down. And one is exponential and one is linear, obviously. Okay. Complete 1 and 2 and compare each. Okay. So let's go ahead and move on to that. Okay. So now we're going to move on to graph these. So let's fill in the tables. So remember, you have your calculator if you need to, for example, well, let's fill in the first table. The first table should be quick because it's 2 times x. And x as a number is -2 through 3. So let's see. This is -4. This is -2. 0, 2, 4, 6. All right. Let's do this one. And this is going to be our first challenge. We want 2 to the -2. 2 to the -2. What is that? You can pop that into your calculator if you want, because it's going to be a decimal number. So what is 2 to the -2? Okay. And I believe this is 1/2, so that'll be 0.5. 2 to the 0, or any number to the 0 is, of course, 1. And that's going to be an important fact for us. Yeah, 2 to the 0 is 1. You could verify that on your calculator. It's 1. 2 to the 1, 2 squared. Oh, that's easy. 2 to the 3rd, 8. Okay, so now let's take some time and plot those. Let's plot the points and graph the line, and then we're going to graph the exponential graph too. I'll do it in 2 separate colors. Okay, so hopefully you've plotted all these points for the exponential functions. Obviously, it's going to just grow really quickly. It's going to take off. But let's look at the negative side. So for on the domain, on the positive side, it's just going to take off. We can see that already. On the negative side of the domain of the x-axis, it's getting smaller and smaller and smaller, right? Will it cross over into the negative side of the range? In other words, will it cross over into the y-axis onto the next side, negative side? What do you think? Okay, Gabriel's already saying no. Does anyone else agree with him? Or think about, well, let's see. Let's experiment for a little bit. Let's all do this together. 2 raised to the, let's try negative 100. Right, so that's very much negative from where we're looking at. And let's see what we get. Yeah, this number is in scientific notation. Remember scientific notation? And it's to the negative, the exponent is to the negative 31. So that's, what is it, like 30 zeros in front of this 7. Remember that? There's 30 zeros in front of that 7. So there's a 0, the decimal point, then 30 zeros, then the 7. That's an extremely small number, right? But is it negative? Nope. Let's try 500. 2 to the negative 500. Oops. I want 2 to the negative 500. Or maybe that's just beyond, yeah. I went too far. This calculator can't give me that number. How about 150? 2 to the negative 150. 7 point. But look at that exponent. It's to the negative 46. So that's 45 zeros in front of the decimal. Then that's 7. Extremely, extremely, extremely small number, but it never becomes negative. It's just never going to touch the negative. And that means the values are always going to be positive. All right, now the fun part. Let's try to connect these points with a smooth curve. And my point is, it's going to get infinitely close to 0, but never going to hit it. And on the other side, it's going to do that. Okay? So this y-axis, this x-axis, not the y-axis. This y-axis is going to be, we're going to give it a special name. It's going to be called an asymptote. Unfortunate name, but it is an asymptote. And an asymptote is a line that exists that you never cross. It's just going to reach infinitely close to it, but never hit it. It's never going to cross over. It's never going to reach 0. It's just going to get infinitely close, but never touch. Okay. And on the other end, what do you think is going to happen here on this part, where it's just growing bigger and bigger and bigger. Is it ever going to hit a spot and that's never going to touch, or is it just going to grow? What do you think? Is it ever going to, like, is there an imaginary line up here that exists that it never hits this way? Or do you think it just grows past that? It just goes on to infinity. Yeah, it goes past it. It's just going to grow, as far as you want. On this side, so on this side, it grows ever bigger, bigger, bigger. And on this side, it just gets as close as you want to zero, but never crosses. Okay, so that's why this is pretty interesting. Okay, so now your turn. Describe some of the differences you see between the linear and exponential functions. Okay, so I'll give you some time to think about that. We know a lot about linear. Now we're learning some stuff about exponential. Okay. Okay. We can answer this question without entering in. Use the table. We don't have a table feature on these calculators. If the graph, but we do know this. Determine if the graph will cross the x-axis. Explain your reasoning. So we talked about this. Is this graph ever going to cross the x-axis down to the negatives? No. So let's say g of x never crosses to what is it? Y less than 0. So it's never going to cross down there. Let's just leave it at that. Describe what happens to the value of y as the value of x decreases. So we just talked about that. What happens to the value of the function as it gets more and more negative? It gets infinitely close to what number? 0. It gets as close as you want to 0, but it's never going to hit it. Okay. All right. So we're going to move on to this next table. And this really describes what a exponential function is. Okay. So exponential function is written in this form, a times b to the x. This is kind of like y equals mx plus b, but for exponential functions. A times b to the x. And here's a few conditions. This a value that you're multiplying b to the x by, it cannot equal 0 for obvious reasons. 0 times anything is 0, right? We don't want this thing to just be 0. So a can't be 0, and b has to be greater than 0. So this b value has to be greater than 0, and b cannot equal 1. And that's for obvious reasons also. 1 to any power, so 1 to the 8th, 1 to the negative 3rd, 3 rather. 1 to anything is always 1. And if it's just 1, it's just going to make a line. And we don't want this to be a line. We want it to be a curve. Okay? The graph of the exponential function increases or decreases rapidly. That's the important part here. Underlying rapidly. So in this case, it grew very quickly. And we just use the number 2. And that's actually brings up a famous um, a question. How did it go? You can either receive $1 million, or you can start with a penny on day 0. Then every day you make twice as much each time for the rest of your life. And you want to take the twice as much than the day before for the rest of your life instead of the $1 million, because it grows quickly to the point where, soon you'll be making, 2 million, 4 million, etc. day after day. All right. And an exponential function graph will always have a horizontal. So that's the part we were talking about here. And the word is asymptote. That's how you spell it. Asymptote. Asymptote. And in case you're wondering, okay, what is an asymptote? It's an imaginary line. Oh, it's an imaginary line. It's going to explain it right here. The asymptote is the value of f is the value that f of x approaches at x as x gets either very large or very small, and can be thought of as an imaginary line. So in the case of the graph we just did, the asymptote is the x-axis. It's this imaginary line that exists that it never crosses. It's a boundary. So the asymptote is this, in this case, is this line. Okay, write that down. So make sure you write down that the x-axis serves as the asymptote. It never crosses it. And we'll get into how do we find the asymptote and all of that other stuff in the coming days. Okay. So based on the description of an asymptote, what appears to be the horizontal asymptote for g of x? Well, it's going to be y equals 0. Yeah. This line at y equals 0 is the line it's never going to cross. Also, it's called the x-axis. Y equals 0 is the x-axis. Okay. All right. So we've kind of defined a few things. We know what to look for in the equation here. Let's flip this page and practice a little bit. So we're going to look at 1, 2, 3. And we have an exponential function and the graph are written. Sketch a line to represent the asymptote and write the equation of the line. If necessary, use a graphing calculator for help. Okay. So here's this f of x equals -1. So this is your a value. And 3 is the b value. Okay. And then just study the graph. Study the graph. So this graph is decaying, it's decreasing. Actually, this is decaying. This is Um, where does it appear to approach but never cross over? At the top. Does everyone agree? How would we describe this line here? Y equals something. Would you all agree it's y equals 0? It's never going to cross over the 0, basically. Never will. So it's going to be y equals 0, which is the x-axis, basically. Okay, in this next one, what's our a value for g of x? 4. What's our b value? 1/4 or 0.25. Okay? And this is the graph that goes with that. Again, what does it appear to approach but never cross over? What number? 0 again. You see how it's just doing that, but it's never going to cross over? All right. This one I'm going to do one new thing. I'm going to put 1 times. It's 1 times 2x and then plus 2. 1 times 2x and then plus 2. So our a value is 1. Our b value is 2 and then plus 2. Got this plus 2. So look at this graph. What does it appear to approach but never cross over? It's not 0 this time. Well, what do you think? 1 or 2? 2. Yeah. And I'm glad most of you grabbed your a ruler, because if I draw a line here, it's never going to cross over 2. So the asymptote is y equals 2. Which 2 do you think affected that? The 2 that's the base number 2, in other words, the b value, or the number that we're adding? What do you think pushed it up to 2 instead of 0? The 2 here in the base or the plus 2? Because it's not crossing at 0, right? It's not like these where the asymptote's at 0. It got pushed up to 2. The plus 2 there basically did that. So that's always going to affect where the asymptote goes if you add or subtract something. All right. Let's look at the last part. 4 through 7. Alexis, can you read where it says Sean?
Sean currently has $10 saved and would like to get more savings over the next 7 months. His 2 potential plans for saving are described below. Use the 2 options to complete 4 through 7.
Okay. So let's start with option 1. We'll fill in the table for option 1. What type of function is represented in each option? Well, 1 is y equals 20x plus 10, right? So he's going to get $20 monthly, and he started off with 10. Okay. Anything else? Nope. All right. What kind of function is this? Is it linear or exponential? Linear. Okay, then option 2, let's look at that one. So option 2, what do we have? Doubling the amount in savings each month Remember, he started with 10. So this one is y equals 10 times 2 to the x. So the doubling is the 2 to the x part. What do you think the 10 is? What does that 10 represent? What did he start with? 10. That's what he started with. Option 2 is clearly not linear, but it's exponential. Okay, so now we're going to fill in the table. Let's start with a linear one. Okay, so let's start. Okay, so we got option 1. Let's get the values for option 2. So this is going to be 10 times 2 to the 0, and that's 10, which makes sense. At 0, you started off with $10, right? And then let's do the same thing, except we're going to replace the exponent with 1. And that gives us 20. And now let's replace the exponent with 2. So up arrow, move over to 40. And then 380. You can probably guess what 4 is going to give us. Follow the pattern. And then we want to double that 160. Okay. So let's go ahead and graph this one. I'll do this one in red. Okay, so starting with $10, then you have 20. Make sure you're graphing this. And then 40. And then at 3, it's 80. So somewhere between month 2 and 3, you actually start making more money with this plan. And then 4, it's 160. And then 5, it's can't even, this graph doesn't even go up to 320. So, okay, so let's plot these points. And this is option 2. Okay, so check in with your partner and answer questions 6 and 7. 6 and 7. Work with your table partner to answer those, and then we'll re-meet. Okay, guys, let's finish it. Let's finish this up. Number 6. Which option will result in Sean saving more money? Explain. Obviously, option 1, right? No? Option 2? Okay, option 2. Because what's happening to his money each month? It doubles. Okay. So summarize the main difference between Sean's two saving plans. Option one. What's happening to his money with option one from month to month?
Adding by $20.
It's adding by 20, right? Yeah, it's increasing. Let's say that increasing by $20. Option two, doubles what Sean made the month before. Remember last year we talked about compound interest and you made money on the money that you had the time before? That's basically what we have here. And compound interest, if you save money and just kind of leave it there, we're talking about 20, 30 years. Those last few years you keep it in there, you're making big money because it's based on the amount of money you had, the time before. And it's increasing based on that, not a fixed amount. So, yeah, we're going to get into compound interest again. All right, so let's get started on this assignment.